So I hope you have now a pretty clear view of the portfolio and you are able to understand the NPU used, the route scale you can get, the bandwidth it offers, the different type of interfaces available, but also the features you can expect on each of these routers. Let's take a few minutes to study the modular chassis. We described all the line cards extensively before, but some important aspects relative to the chassis themselves need to be described. We have 4-slot, 8-slot and 16-slot options, and all of them share the same route processor, system controller, power supply, and they can mix and match all types of line cards. But there is some specific components correlated to the size of the chassis itself, the fan trays and the fabric cards. The chassis is based on an orthogonal design. That means you insert the line card horizontally in the front and you plug them directly to the fabric cards inserted vertically in the back. And finally, each pair of fabric cards is covered by one fan tray. No mid-plane or back-plane, they are directly connected to optimize the cooling of the system. That means the fabric card size depends on the number of line cards you can plug to it. And similarly, the fan tray size depends on the fabric card size they are supposed to cover. That's why these components are specific to each chassis. Inside the router, you have 6 fabric cards, and their role is to route internally the cells between different NPUs of the line cards. They are not aware of the concept of IP stream or flow. They are just quickly routing cells to their destination based on what has been programmed on the internal packet headers. We do have 2 different generations of fabric cards and fan trays. It's mandatory to pair fabric and fan of the same generation, V1 with V1, V2 with V2. The first generation is based on FE3600 ASIC and supports Jericho and Jericho Plus. In 4-slot chassis, each of the 6 fabric cards contains one single FE3600. It's 2 for the 8-slot chassis and 6 for the 16-slot. Here, I'm representing one line card connected to the different fabric engines and fabric cards. It's a full mesh, and each NPU is 2 hops away from other NPUs. And that's just one line card, so you can imagine how it is for 16 slots. We need the second generation of fabric card and fan tray to support the new line cards based on Jericho 2. And they will be backward compatible with Jericho and Jericho Plus. I repeat because it's important. You need to operate V2 fabric card with V2 fan trays. Also, we don't support in-service migration from V1 to V2. You'll need to shut down the router electrically before proceeding to the migration. In the V2 fabric, we have a new generation of engine called Ramon, and we will need 1, 2 or 3 of them per card for 4-slot, 8-slot and 16-slot respectively. Please note that the 4-slot version is not shipping today. It is in the roadmap and planned for the end of the calendar year. I would like to spend 5 minutes on some key concepts related to the NCS 5700. If you consider a chassis, once you operate it with fabric cards and fan trays of second generations, you have 2 possibilities. On the left, you can use a mix of Jericho, J+ and J2 line cards, and it will be a very common situation considering we have already more than 40,000 NCS 5500 routers in production today. So we have an important install base. In such situation, the chassis will be configured and operated in what we call the compatibility mode. That means the packets are specifically labeled inside the router with internal headers to be understood by the 3 generations of line cards. A packet can be received on a Jericho card and transmitted to a Jericho 2, or vice versa. We need to guarantee a certain level of compatibility between the NPUs. Some functions are local to the card, so they will benefit by the higher capability of J2, and some others are global to the chassis, and therefore they will be limited by the lowest common denominator. That's the reason why some features and some improvement will not be available in compatibility mode. It will be a case-by-case discussion. On the right, we have a chassis with exclusively J2 line cards. On this one, we can enable by configuration what we call the native mode, and that will unleash the full capability of the J2 ASICs. We introduced the J2 line cards in iOS XR release 7.02 in February 2020, and it's only a compatibility mode version. Regarding the level of features and scale supported, it will be a phased approach. That means we will introduce more and more functions release after release. In 7.02, we are supporting core and peering features, as they were present in iOS XR 6.5.1 and Jericho Plus. Same features, same scale. The features supported include L3 VPN and multicast in the global routing table, but not layer 2 functions at all. No bridge domain, no VPN, VPWS, VPLS, BVI, etc. Also, no lawful intercept, no timing, no power replication, and no MLDP. Finally, we have a limited set of features regarding BFD. In 7.2.1, we'll introduce a native mode with the same set of features we had in compatibility mode in 7.0.1. And at the same time, the compatibility mode will be enhanced with the addition of more features in Layer 2 VPN, and timing. And we'll start covering the requirements for aggregation roles. Then, release by release, you will see that compatibility mode will complete the feature coverage for aggregation, and the native mode will progress too. In 2021, you will see we reach support parity between compatibility and native mode, and then the native mode itself will take precedence and be step-by-step more capable. Among the features coming in native mode, we'll introduce the capability to carve the Jericho 2 modular database in different profiles. That way, you will be able to make the product more scalable for specific roles, more L2 or more L3, for example. Here, I'm showing you can already take a look at the default MDB carving we use in 7.02. You can see with this show command what is allocated for each resource. It's now time to dig a bit deeper into the internals of the NCS 5500. In this section, we'll talk about ingress buffering, we'll describe the concept of virtual output queue, and also we'll go into the details of the scheduling mechanism used for unicast traffic. I always take the SR9K as a comparison point since it's the most successful platform we have in the service provider field, so people know it very well. But it applies to many other products, both at Cisco and other vendors. So in a 9K, we have a two-step lookup architecture. When a packet is received, the ingress NPU will buffer it, apply the features, perform a lookup to figure out which specific egress NPU it should be sent to, and then the packets are split in cells, travel through the fabric, they are reassembled on the egress side, where they will be buffered a second time, the egress features will be applied, and finally a new lookup will be performed to figure out the interface or sub-interface the packet needs to be sent to. Then the destination MAC address will be positioned, the MPLS labels too, and the packets will be sent. In NCS 5500, the large majority of the features will happen in the ingress side, even if the functions are applied on egress interfaces. So consequently, when a packet is received, it will be stored in the ingress buffer, the lookup of the destination will be performed, and if a specific egress treatment is needed, the NPU will update the internal headers of the packet, so we have a single lookup in ingress, and the buffering is done there. It will include encapsulation decision on the egress interface. Even if you apply a QoS configuration on your output direction of your egress interface, the packets will be actually stored on the ingress buffers. And it will be only the discussion between all the NPU schedulers that will translate the QoS configuration into actual packet transmission decisions. That's why we have only the deep buffers on the ingress pipeline. So I'm showing the packet memories for Qumran MX, Jericho, and Jericho Plus here. On the ingress side, we have the 16 MB of SRAM on-chip buffer and the 4 GB of GDDR5 off-chip. You can double these figures for Jericho 2. On the egress side, we have a smaller buffer of 6 MB, just 3 per core. This buffer is not meant to store packets for a long time, but only to differentiate unicast, multicast, high and low before the packet serialization. In normal situation, the packets are received and stored in the on-chip buffer. That's the case for the vast majority of the packets. If we experience an egress queue congestion, the packets will be stored in the large off-chip buffer, 4 GB for Jericho and Jericho Plus, 8 GB of HBM for J2. That's why we call it an hybrid buffering architecture. And the mechanism of moving packets to external buffer is named an eviction. Note that the level of granularity is the queue, not the port. With this approach, we don't have any head-of-line blocking issue. If a queue is congested, it's moved to the external buffer, and once the congestion is over, the queue is moved back to the on-chip buffer. For your reference, I'm detailing here the level of congestion used to decide of the eviction of a given queue. Now, the packets are reassembled from the fabric on the egress NPU, and they are ready to be sent to the egress port. Again, we have a very small amount of buffer here, because we are not expecting to store packets for a long time. The QoS decision has been executed already, and if a unicast packet needed to be dropped, it has been done on the ingress side. We'll explain why in a few minutes, but still, it's important to identify and differentiate the unicast from the multicast traffic, and to assign them two different levels of priorities, high and low. I will come back after we explain the treatment of the multicast packets. So, what is a virtual output queue? First, the concept of VOQ is nothing new. It has been around for a long time and used in multiple products. That includes ASR 9K, NCS 6000, and many others in the Nexus family. What is new is the fact that we are not limiting it to the fabric, but it's now extended to the NPU. When a packet is received in ingress, it will be classified, even if no QoS is configured, and the NPU will determine the egress interface and the encapsulation, MAC address, MPLS labels, GRE headers. So the ingress NPU knows everything about this packet, and it will store it in a local queue gathering all the packets for the same egress port and the same class. By default, this local queue will be on the on-chip buffer, and if we have too much packets in it, it will be evicted to the off-chip buffer. I'm representing the queues on the egress port with dotted lines because they don't physically exist there. They are actually present in the ingress NPU. On egress, we just have 4 queues per physical port: high, low, unicast, multicast. So, for a given egress port, like this 100 GiGi 0700.2, we are creating these queues local for each ingress NPU. That way, 2 packets received from the left and targeted to this particular .2 subinterface will be stored in their local VOQ created for 700.2. One on the NPU 0 of line card 0, and another one on the NPU 1 of line card 1. And even on the same line card and NPU of our egress interface, we are creating this VOQ on the ingress pipeline. For every new interface we configure, we create the VOQ structure on all ingress NPUs, whether or not the packet is meant to be received there, targeted to the destination. The system does not allocate a specific amount of memory for each VOQ, but it creates a structure to be able to store them in the right queue if a packet is received. When someone familiar with the SR9K architecture asks me how many queues does the NCS 5500 support, it's very difficult to answer. You are comparing very different things because, of course, it's dependent on the number of egress ports. I believe the official answer is 96,000 queues, but what are we talking about exactly? Apples, oranges. For your reference, I'm showing here the output of a show ceph command, and it's possible to track the VOQ for a particular destination. I suggest you take a look at the troubleshooting session my colleague Andrej presented in CiscoLive Barcelona. It's very good if you want to learn how to track all this step by step. The reference is BRK SPG 2165. If a queue is congested to the point of creating tail drops, these drops will happen in potentially all ingress NPUs, and the counters will be distributed everywhere, on all line card, all NPUs, and even all cores. That's what we call ASIC instances here. This other show command can be used to understand the mapping between ports and ASIC core. It's very important to understand it because we may have architecture where we have more ports on core 0 than core 1. That's typically the case of Jericho Plus, 900 gigabit per second for forwarding capability. That's 9 ports, 100 gig. It's not possible to share equally 9 ports between 2 cores. Earlier, I purposefully used an example of an L3 subinterface to show that a VOQ is not related to a physical port. It could be L2, L3, main interface, VLAN, bundled subinterface, it could be BVI. All these are what we call attachment points. That's where we allocate VOQs. And now, your favorite part of the presentation, I'm sure, the life of the packet. More precisely, we'll follow 3 different unicast packets received on these 3 different NPUs. They are all targeted to the same destination, but 2 of them are voice and 1 is web browsing over HTTPS. On each of these NPU, the packets are classified and a lookup is performed. Packet A is web, so it will go to VOQ 0 of my egress port 0700.2, while B and C will go to VOQ 7. These VOQs are on each ingress NPU. They are distributed and they don't physically exist as queues per se. It's just a space in the memory where the packets are stored. So we positioned internal headers on this packet and we kept track of their position and the size inside the memory. Each scheduler present on the TM part of the ingress pipeline will inform the egress scheduler of NPU 0 line card 7 that he has a packet to send. Again, 2 for VOQ 7 of the port and 1 for VOQ 0 of the same port. Basically, each ingress scheduler is making a request to the write to transmit a packet. And it will not do anything until it receives a positive answer. So if we have no QoS configured, the egress scheduler will take a round-robin decision. But let's imagine that we have QoS configured on the egress port, and we define the VOQ7 as a low-latency, strict priority queue, and the VOQ0 as just a default queue in a class-based weighted fair queue design. So the egress scheduler has now two requests of equal importance for two voice packets, and the round-robin transmit decision inside this priority queue picks NPU1 LC1 as a first, so the scheduler sends a grant, a permission token if you want, to transmit X amount of traffic from VOQ 700 gigi 0700.2. Ingress VOQ scheduler of NPU1 LC1 received this permission and now can split the packets into cells, spread them all over available fabric engines, and the cells are routed by the fabric, received on the egress pipeline, they are reassembled into the form of a packet, and another classification will happen here, but only to identify if the packet is unicast or multicast, and what is the priority. Since it was a priority queue, it's considered to be high. Finally, the packet is transmitted to 0700.2. Then the algorithm selects the second voice packet B, which is also in priority queue. The egress scheduler sends a token to NPU LC0. The packet is transmitted through the fabric, classified again as high priority unicast, and the traffic is finally transmitted. Finally, our HTTPS packet is given the right to be transmitted too. But what is interesting here is the egress classification. Since the packet is not from a priority queue, it will land in a unicast low priority on the egress port buffer before being transmitted. So why should you care? You'll understand in 10 minutes after we cover multicast. Multicast. In NCS 5500 systems, the multicast replication, the trees, the branches, are performed in two places. In the fabric first, to send a copy to all ingress NPUs interested in the flow, and each egress NPU in a second step to create different branches to all the interfaces connected to the receivers. Inside the chassis, the multicast packets are handled in a very different manner than their unicast brothers. And the key difference is the fact they are not scheduled. That means they will be transmitted without receiving the authorization from the egress scheduler. It will have direct consequences on the QoS behaviors. It's very important to pay attention to this part. Multicast packet is not handled, not even counted by your output service policy apply on egress interface. So, why it is not scheduled? Let's imagine a model based on an egress scheduler receiving a request to transmit a multicast packet. If one port only is congested, this egress scheduler of NPU0 line cards 5 will not give the token, and therefore the ingress scheduler will be stuck, even if all other egress gave permission to transmit. One single branch could block an entire tree. That's why when a multicast packet is received, the ingress scheduler will auto-allocate a token to itself and send the traffic to the fabric where it will be replicated. So we will not use virtual output queues, but instead fabric multicast queues. We have 4 different levels, and one will be mapped to the high priority multicast when the packet will be received on the egress port buffer. The 3 others will be considered to be low priority multicast. Whether your multicast packet will be high or low priority can only be influenced by a classifier on the ingress port, and not via the egress service policy. In ingress, you classify your multicast traffic based on DSCP field, for example, or maybe an access list, and you mark them with a specific traffic class. If it's an important stream, you want it to be treated as high priority, so you will use traffic class 6 or 7. Automatically, the system will map these traffic class values to FMQs. 0 and 1 to FMQ 0, and up to TC 6 and 7 to FMQ 3. When your packets are received on the egress pipeline, the classifier will use the FMQ value to move the packet into the right queue of the egress port. Only FMQ3 will be high priority. The 3 others will be treated as low. So you influence how your multicast packet will be treated on the egress pipeline by changing the configuration in ingress. Let's imagine I receive a multicast packet A and we consider it to be of low importance. This packet will be replicated to two egress interfaces connected to NPU 0, line card 5, and NPU 0, line card 7. You configure an input service policy, classifying the multicast packet and marking it with a traffic class 1. Automatically, it will map TC1 to FMQ0 and transmit the packet to the fabric, where it will be replicated. A copy of the packet is received on the two egress pipeline. Since it's FMQ0, they are storing the packet in the low priority multicast egress port buffer before being sent to the destination. Now, if my stream is very important or valuable, I will mark it with traffic class 7. It will be mapped to FMQ3 and it will land in the high priority multicast queue on egress. But again, you can ask me, why should I care? And it will come clear now. If you have multicast only, you should not care at all. The packets being tail-dropped by a congested port will be discarded in the ingress pipelines. Maybe you want to make sure that locally originated packets, the ones coming from your routers, are treated with a high level of importance, and it's always the case. These type of packets are stored in unicast and multicast HPQ when they arrive on the egress port. Now, if you have multicast in the picture, it's not the same story, because multicast is not playing a fair game. But the multicasts are not scheduled and they will be transmitted to the egress NPU regardless of the congestion of the outgoing queue. That's why you need another place to differentiate and discriminate unicast from multicast, and between them, important and less important traffic. That's the job of these 4 queues on the egress port. We need a tiebreak to decide what is important and what can be dropped. If you have traffic in a high priority queue and it competes with low priority queue, logically, you will always give precedence to high. But if you have a conflict between unicast and multicast of the same level of priority, then we will give 80% of the port bandwidth to unicast and 20% to multicast. Today, it's not possible to change this ratio, but I've seen plans to make it configurable in the future. If you have important multicast traffic, you don't want it to be dropped in case of UDP amplification DDoS attack, for example. So it's important to mark it in ingress to make sure it will land in the HP multicast queue on the egress. Another important aspect you may need to keep in mind: you cannot count multicast traffic in your QoS policy. So you will need to define your rules accordingly. You got it. QoS is a key difference when compared to the two-step buffering systems like ASR9K. And I will briefly scratch the surface of this very wide topic now. And even if they are both speaking iOS XR, if you take an ASR9K QoS configuration and you copy and paste it in a NCS 5500, chances to see it successfully committed are very slim, almost impossible. It's very likely you will save much more time going to the whiteboard and discussing the intent of the existing policy to redefine it end-to-end, rather than just trying to translate them. We support ingress classification based on IPPREC, DSCP, MPLS-EXP, .1Q, DEI, COS, but also access list. And you can remark the fields in the ingress direction. Also, you can apply a polisser, a rate limiter if you want, in ingress. So far, nothing much different than we have on ASR9K. It's a different story for the egress direction. First, you won't be able to classify traffic based on the fields I mentioned earlier. It's not possible to match DSCP expedite forwarding or MPLS EXP7 if you apply this policy in output. You will not be able to commit the configuration. You can only match headers that are internal to the box. For instance, the traffic class I mentioned during the life of the packet earlier, the quote group, and the discard class. I'll give an example in a minute. Second, you cannot do policing in egress, but only shaping. To overcome this limitation, we can mimic the behavior of a policer using a shaper. The trick is to configure a very small queue limit on the policy. That way you have minimal buffering done before tail dropping. The difference with a rate limiter will not be noticeable, particularly on high-speed interfaces. So what can I do if I want to match certain traffic types on egress and assign them to specific queues? Here is the logic we use on NCS 5500, and you will understand why you cannot directly use configuration from 9K and apply them on these routers. You will have to rethink the QoS policy entirely. I can't match DSCP expedite forwarding on egress, but I can match traffic class. So we will break it in two parts. First, we create a policy in ingress, matching DSCP-EF, and it will mark the packet with a traffic class 7. Second, we'll create an egress policy, matching the traffic class 7, and assigning to the priority queue and giving this packet the low latency treatment we want. You got the idea. We will mark internally the ingress packet with a specific field, a color, the traffic class, and we will use this coloring to match the traffic and assign it to the appropriate queues. With the same logic, we can mark the packet in ingress with a queues group, and we will use this information to do egress remarking. And finally, it's possible to set a last flag in ingress named discard class that can be used for the wread. You see, it's getting very different from traditional platforms like 9K, and we are only scratching the surface here. I give you an example to illustrate the mechanism. I create an ingress policy, pol1, with multiple class maps matching IP-prec 1, 2, and 3, and they are marking traffic class 1, 2, and 3 respectively. On the egress side, I have another policy matching the traffic classes, TC1, 2, and 3. The class TC1 is a priority queue of first level, level 1, and we shape to 20% of the interface bandwidth. If I want to make it behave like a policer, I will define a minimal queue limit here. TC2 is a class-based weighted fair queue, and this shaper is given 50%. If you don't define a queue limit here, your shaper is given 10 milliseconds of the interface speed. Finally, TC3 will get 30% and nothing configured for the class default. Just for your reference, I'm presenting a layer 2 example, and this one is interesting just to illustrate the difference we have with other platforms. Since you can mark the traffic with internal flags, you may end up with potentially multiple coexisting output policies. See, here we have one for the queue assignment and a second one for the remarking in egress. I will stop here for QoS. Again, it's a huge topic. It's usually the main point I bring to my customers' attention when we are introducing NCS 5500 in their network. But it's not the only one. Where can we position the NCS 5500, and what are the key points we need to pay attention to? I know everyone wants to put things in boxes and assign roles. That simplifies the selection process when it's time to refresh or extend the network. But I'm afraid nothing in life is that simple. If you ask me, can I use NCS 5500 for peering, core, aggregation, edge? The answer is yes. Can it be done for your particular edge? Then the answer will be it depends. It depends on many parameters. What are your requirements in terms of port density today and in 5 years? What are the features that you need in details and what scale is expected? Do you need debuffers? Does the power consumption a key factor? And I'm sure the answer is yes. Do you need to keep one single operating system to simplify your end-to-end service deployment and management? And of course, the number one question for your purchase department, the price. If I take a simple example for a peering role, it's very likely the NCS 5500 can cover all your bases. But even here, it will be important to make sure you select products with large FIB capability and BGP flow spec support. Another example, Edge. Here it will be important to understand precisely the features expected and the scale. How many sub-interfaces with QoS, L2, L3 VPN, how many MAC addresses, how many routes, etc. Many technologies are supported, but certainly not at the same level of an SR9K. That remains the de facto platform of choice for all edge functions. So, no simple rule of thumb. Talk to your Cisco representative and they will guide you. Let's cover all the things that you need to think about. I mentioned QoS earlier and said you may need to go back to the whiteboard and identify all the flows transiting through your network and how you want to treat them, rather than trying to translate existing configuration. I know it's time and resource consuming and it's not a trivial exercise. Another important aspect, remember that multicast is not scheduled and it's not seen by your egress policies. The supported scale for a given feature may be dependent on what else is configured and used, simply because they will store data in the same memory space and they may compete for this resource. So it's important to track the memory utilization of these diverse resources, and we'll briefly show you a few shortcomings just after this section. Let me cover the other bullets here in individual slides. In Jericho and Jericho Plus, we have 256,000 entries in the statistics memory. It's not that much if you consider what needs to be counted in a router. That's why some features are not allocated counters by default. For example, you don't have counters for LDP or RSVP signal LSPs. If you type in the CLI show MPLS forwarding, it will not give you packets and byte statistics for the LSP. We have them for segment routing though. Another one where we don't have counters for is the WRED packets drop. Also, by default, an access list only counts the denies entry, but not the permits. It can be changed with a specific hardware profile. By default, the multicast forwarding is not counted. It's possible to create an access list describing your groups of interest and use another hardware profile to enable the counters for these particular groups. Keep in mind, it works only in the global routing table today and not in VRFs. Talking about hardware profiles, we are using them in multiple opportunities to optimize a resource for certain roles. It's fine in most of the cases, but it may happen that the carving of this resource could lead to a conflict. We have many profiles and we documented them in the blog post on xrdocs.io, and there you will also find details on the potential conflicts between them. This other one is simple, but you may lose a lot of time if you are not aware of it, and if you are configuring, for example, an NCS 5582 mode for the first time. Actually, it's valid for all platforms who support natively 25 gigabit Ethernet. These interfaces can do 25, 10, and sometimes even 1 gig Ethernet, but by default they are configured for 25. So if you plug an SFP or SFP Plus optic, the port will not go up until you configure this particular hardware module quad. And the configuration is applied to a group of 4 ports. That's why we talk about quads. You just need to configure 10 and it will work for both 10 and 1. FEC and ECMP FEC. That's another important topic to consider before your deployment. The FEC table in Jericho ASICs contains the next stop information. It's a 128,000 entries memory. The routes are present in LEM, LPM, or ETCAM, and they use a pointer to a FEC structure. Where the next stop is reachable through multiple links, that involves load balancing, and in this case, another memory is used, ECMP FEC. It's a subpart of the FEC resource and it's only 4,000 entries large. For IP-only network, it's not that important, but for MPLS, this size can become too small very quickly, particularly if you have a lot of prefixes binded to labels. Many solutions exist to overcome this, or at least reduce this limitation, and some have been described in this breakout session, BRK SPG 3292, but the first one that comes to mind is to recommend the limitation of the binding to only the router's loopback. It's a well-known best practice, but I've seen a lot of networks where it's not the case and they are allocating labels for all the links addresses. The last tip for today is related to the VRF. It's mandatory that you don't keep the default label allocation mode in iOS XR, the per prefix mode. Otherwise, you may exhaust the resource very quickly. We recommend instead that you use the per VRF or per SC mode, depending on your needs. Here again, I'd suggest you take a look at the article that we wrote on xrdocs.io that describes these aspects in details. And the last part of this deep dive is the resource monitoring. We covered in detail the memory used by the forwarding block in ingress pipeline, the LEM, LPM, ETCAM. They contain essentially prefixes and point to next stop data, FEC and ECMP FEC, in case of load balancing. This hierarchy works well with Ceph software infrastructure. If we have routes learned from multiple sources, for example multiple BGP peers, we store the routes in one database and the multiple next stop in the FEC. If the best transit goes down, we don't need to reprogram all the routes, but only change the pointer to the second best next stop. That's typically how is implemented BGP core, which is by default enabled in iOS XR. In the FEC, we have information on the egress interface and the VOQ, but also a pointer to an encapsulation database called EEDB. When the packet reaches the egress pipeline, it will use this information in the EEDB to remark the MAC address, swap the MPLS labels, impose the GRE headers, etc. All these resources should be monitored constantly, and it can be done with CLI, but also streaming telemetry, but not SNMP. We don't have any OID for this. The system will trigger error message in the console or syslog if you exceed certain level of usage. We use a middleman to program the hardware It's called the data plane abstraction, or DPA, and you will have yellow alert triggered at 80% and red at 95%. With show DPA resources, you can collect data for each type of information program in the hardware, so routes, access list, statistics, etc. If the resource is full, the DPA will simply refuse to program it, and it will increment the hardware failure count. That's typically the case of this example I picked, trying to program 800,000 routes in the LEM, so more than we can accept. To monitor the utilization and also the estimation max entries, you should use show controller NPU resources with the many options available. I'm showing here for LEM of each NPU, and you have the max number of entry possible, what is used, and what are the consumers of the resources, IPv4, IPv6, MPLS. And same for LPM here. You'll notice that the max entries is a variable number since this memory is algorithmic. It may vary depending on the routes currently programmed. Finally, you can collect or stream all this with young data models. Let's conclude this virtual breakout session on NCS 5500. Thanks a lot for watching the deep dive. If you want to complete your education, I already shamelessly plugged the team website, the xrdocs.io. We have a dedicated section for NCS 5500 tutorials, and it contains a lot of articles. And we add more and more content every month. So take a look, you won't be disappointed. NCS 5500 is a very popular router family now. It's popular, of course, in service provider field, but not only. We have customers in enterprise, education, government, industry, etc. The role depends on your decision. We provided you a lot of information to let you make an educated choice. Also, we presented you the key differences with more traditional platforms like the CRS or the SR9K. I hope it gave you a much better understanding. Thanks a ton for watching, and take care.